In this video, we're going to ask the question, what is centripetal force? Centripetal force answers the question, what keeps objects moving in a circle? The definition of centripetal force is a net force that's directed towards the center of circular motion that keeps an object moving in a curved path. We'll first take a look at some examples where there are single forces that are playing the role of centripetal force. Here we have a satellite orbiting the Earth, and the force that's playing the role, R-O-L-E, the role of centripetal force here is Fg. So it's important to remember that centripetal force is not another force like gravity force or normal force or friction force, but rather it is a role that any force can play. Here we have a car that's rounding a curve. And the force that's playing the role of centripetal force here is going to be static friction. Even though the car is moving, the wheels are not slipping side to side. So static friction is keeping this car moving in this curved path. If there was no static friction, then this car would, if it started to skid, it would end up going in a straight line. Here we have a ball tied to a string, and we're swinging this ball around in a circle, and the string is what's keeping it in a circular path. So the tension force here is playing the role of the centripetal force. This is a barrel ride that you might see at a amusement park, and it rotates here, as you can see. And as it rotates, the people inside feel like they're getting pushed and stuck against the wall, and that's because as it's spinning, the person has inertia, wants to keep going straight, but the wall is exerting a force on the person towards the center, and this would be a normal force since it's the wall pushing on the person. Next, we're going to look at situations where there are multiple forces playing the role of centripetal force. Here we have a roller coaster going around a loop. At the highest point of the loop, there are a couple forces. There is gravitational force, and depending on how fast it's going, there can also be a normal force. And this car is going in this direction here. So as far as the equation, if we were to solve a problem with this situation, here's how I would set it up. We start with the net force is equal to mv squared over r, and we will typically make the direction towards the center positive. So all the forces towards the center, so we have Fg plus Fn equal to mv squared over r. And so this is how you would set up the equation for a problem like this. Here we have a ball tied to a string, and unlike the first one where we're swinging it horizontally, this one we're swinging it vertically. And then so at the highest point we have gravitational force Fg, and then we also have the tension force. If we pull hard enough, we also have a tension force here. And for a problem like this, to set it up for a mathematical problem, I'm going to start off with net centripetal force equals mv squared over r, and then the Fc here is going to be Fg plus Ft equals mv squared over r. Now, once the ball is swung to the bottom of the circle, we still have tension force that's going up, Ft, and we still have Fg going down, but this time it's down. So Fg this time, Ft, I'm sorry, is going up this time, but Fg is still downward. So to solve this problem mathematically, you would set it up this way. We take the force, Ft, because towards the center, minus Fg. Notice the difference here. This over here was plus, this is minus because in opposite directions, equals mv squared over r. Now we're going to take a look at a situation where you're going over a hill, and our car is up here. And let's say it's going in this direction. Here's the velocity. So the forces acting on this car are going to be gravitational force Fg and Ft. And Ft is going to be a little bit shorter because I know that the net force is going to be downward. So the centripetal force here is going to be Fg minus Fn. and then you can set that equal to mv squared over r. Now let's take a look at what happens if you go over a dip here. So here's a dip, and here's our car. Car's going this way. And we once again have FG, but this time the Fn, the normal force, is going to be greater. And that's because the center of this curvature, the circle right here, is above the car. And so mathematically, we would write it Fn minus Fg equals mv squared over r. Here we have what's called a conical pendulum. So this pendulum right here is swinging around in a circle, forming like a cone shape. And at this point here, we have gravitational force and we have tension force. Okay, so the question is, what force is playing the role of centripetal force? In this case, it's going to be a component of the tension force, because the centripetal force is going to be directly towards the center of the circle. And since the circle is right here, we're going to break this into components. So this has this component, the x component, and the y component. And so the component that's, and let's say this is theta. So the component that's playing the role of the centripetal force here is going to be Ft cosine theta. So as an equation, here's what we would write. We would write Ft cosine theta is equal to mv squared over r. Once again, we're starting with this equation. Net centripetal force is equal to mv squared over r.